So let's see what else we can say about the characteristic polynomial. So we've already seen that the roots of the characteristic polynomial are the eigenvalues of our matrix. Well, remember that the fundamental theorem of algebra says that every polynomial factors as a product of a bunch of terms of the form t minus a root raised to the multiplicity. So theoretically, the fundamental theorem of algebra tells us that our characteristic polynomial factors as t minus the first eigenvalue raised to the multiplicity, which we're going to write for the moment as am sub a of lambda 1, multiplied by t minus the second eigenvalue raised to its multiplicity, am sub a of lambda 2, and we keep going until we get to the last eigenvalue, t minus the last eigenvalue raised to its multiplicity, am sub a of lambda k. So here, lambda 1 through lambda k are the eigenvalues of our matrix. The multiplicities that pop up in this context, so these are the multiplicities of each eigenvalue as a root of the characteristic polynomial according to the fundamental theorem of algebra. These are called the algebraic multiplicities of the eigenvalue. So if we manage to factor our characteristic polynomial, the power of t minus lambda to whatever, that is the algebraic multiplicity of the eigenvalue. So let's look at an example. Here we have a perfectly good 3 by 3 matrix, and someone has been kind enough to factor the characteristic polynomial for us. The characteristic polynomial is t plus 7 squared multiplied by t minus 9. So this immediately tells us that this matrix has two eigenvalues, negative 7 and 9. And the fact that this is factored also gives us the multiplicities. The algebraic multiplicity of negative 7 as an eigenvalue is 2, and the algebraic multiplicity of 9 as an eigenvalue is 1. So what sort of properties does the algebraic multiplicity of an eigenvalue satisfy? There's a size formula. If you remember from the fundamental theorem of algebra, the sum of the multiplicities of all of the roots of a polynomial always equals the degree of the polynomial. So that's exactly what the size formula says. It says if you have all of the eigenvalues of a matrix and you add all of the algebraic multiplicities together, this always equals the size of the matrix. And remember, we have this new thing called algebraic multiplicity, but we had used the term multiplicity previously when discussing eigenvalues, and in that context we called the multiplicity the geometric multiplicity. This was the dimension of the associated eigenspace, which is the nullity of the characteristic matrix. It turns out that this concept is related to the algebraic multiplicity, but this is not the same thing. We have a comparison that always works. So this is bounds for the geometric multiplicity. 1 is always less than or equal to the geometric multiplicity, which is always less than or equal to the algebraic multiplicity. So the geometric multiplicity can possibly equal the algebraic multiplicity, but it might be less, but it will never be greater than the algebraic multiplicity. So let's see this applied in an example. Let's say somebody gives us an n by n matrix, and what they're telling us here is that the characteristic polynomial of this n by n matrix factors like this. What sorts of things can we conclude? Well, we can add up all of the multiplicities. Ooh, and it looks like I've made mistakes here. So the multiplicities in this context are 4, 4, 5, and 8. So if we add these numbers together, we should get the size of the matrix. 4 plus 4 is 8, plus 8 is 16, plus 5 is 21. So I've made a mistake here. So this shouldn't be 3 plus 7 plus 2 plus 8. It should be 4 plus 4 plus 5 plus 8, which is 21. So that's the size of the matrix, 21. And what we can do here is we can organize all of our so-called eigendata into a table. What we're finding with this characteristic polynomial factored is that the roots are I, negative 5, and 9. So we know what the eigenvalues are, I, negative 5, and 9. And we know what the algebraic multiplicities are. They're 4, 4, 5, and 8. So we can include the algebraic multiplicities in our table here. And now the idea is we could ask the question, what are the geometric multiplicities of these eigenvalues? And this is actually an open question. All we know is that the geometric multiplicity is somewhere between 1 and the algebraic multiplicity, but without knowing the matrix, there's not much more we can say here. So since the algebraic multiplicity of lambda equals I is equal to 4, all we know is that the geometric multiplicity of I is some number between 1 and 4. Same goes for negative I. The algebraic multiplicity was 4, so the geometric multiplicity is just some number between 1 and 4. The algebraic multiplicity of negative 5 was 5 here, which means that the geometric multiplicity is just some number between 1 and 5. And the algebraic multiplicity of 9 was equal to 8, which only tells us that the geometric multiplicity is some number between 1 and 8. So we don't have enough information here to conclusively say what the geometric multiplicities are, but we do have a range of possible geometric multiplicities in this context.